Okay, so now let's talk about the rules of differentiation involving functions of different variables. Right, so the keyword here is different variables. So in the section 2, we talk about the different functions of the same variable. Right, they have the same variable x, but here they have the different variable. Right, so one function may be of function x, and the other function may be of function y. Right, so they're different, and to find out how to find out the differentiation of them. So the first thing we talk about, which is very important here, is called chain rule. So chain rule means when you find out the differentiation, kind of like using the chain to take the derivative one by one, and then finally we have the derivative obtained, right? So for example here, if there's a function z equals to f of y, so that means that z is a function of y. But the variable here for function z is y. But y is also a function of x. So y equals to gx. So x is a variable of y. Right? So if this is the case, then we want to find out the derivative of z with respect to x. We know that x is not directly in the function z, right? Because the variable in function z is y. But y is also a function of x. And now we want to find out the derivative of z with respect to x. What we're going to do is to use the chain rule. So first, we take the derivative of z with respect to y, and then we take the dy over dx, and then we multiply them together. Right? From this function, it's kind of like we write the dy in the denominator, and then here in the numerator. So we can cancel dy out, and then find the dz over dx. Right? So this is, in this example, dz over dy is just f prime, and dy over dx is g prime. So dz over dx is just f prime times g prime. And we can use a composite function to express the relationship between z and x. Right? So z is f of g of x. So gx is y, right? So z is a function of y, but y is also a function of g. So we can get rid of the y by writing y as a function gx. Right? So z equals to f of y equals to f of g of x. So this kind of thing, we call this composite function, a function of a function. Okay. So there's an extension. If we have three variables, like z is a function of y is a function of x, and x is a function of w, then in order to find out the derivative of z with respect to w, we again use the chain rule to write a long chain as this, to first take the derivative of z over y, and then y over x, and then dx over dw. So this is just the f prime times g prime, and then times h prime. Okay, so we take the derivative of one by one, and then multiply them together to find the derivative. So for example, z equals to 3y squared, y equals to 2x plus 5. Right, so z is a function of y, and there's no x in z function. There's no x. However, y is a function of x. So actually you can plug in, you can replace y using the function 2x plus 5, and then you plug in 2x plus 5 into this function to find out the relationship between z and x. Right? So this is the idea of composite function. So in order to find out the derivative of dz over dx, we first take the derivative of z over y. So the derivative of z with respect to y is just a 6y, right? 6y. And then we calculate dy over dx. So this is just a 2, right? The derivative of 2x plus 5 with respect to x is just a 2. So this is 12y. And then next we plug in 2x plus 5 here. So this is just 12 times 2x plus 5, which is the result of the derivative. So for the second example, z equals to y minus 3, y equals to x cubed. So again, the dz over dx should be first take the derivative of z with respect to y. So this is 1. And then we calculate dy over dx. So this is 3 times x squared. So the derivative is 3 times x squared. So this is called chain rule, right? So if we have multiple variables and they are related to each other, so we can use the chain rule to plug in the function and to calculate the final derivative by calculating the derivative one by one and then multiply them together. And the second one is called inverse function rule. So if the function y equals to fx is a one-to-one mapping. So this means that for each value of y, there's only one unique value of x that's associated with the value of y. So for example, for a linear function, right, this is y, this is x. For a linear function like this, we know that the definition of function requires that for each value of x, there's only one y correspondingly. Right? But we don't require that for each y, there's only one x. Right? But here, if this function is a one-to-one mapping, so that means that for each x, we have only one y value associated with it. And for each y, we again has only one x value associated. So in this case, we call this one-to-one mapping. For another example, if y is a quadratic function, so for each x, we have only one y, right? But for each y, we have two x associated with it, right? We have two x, x1 and x2 here. So in this case, this is not a one-to-one mapping, because for each y, there may be two x values that are mapped to the same y, right? So only this kind of linear function or similar function is a one-to-one mapping. So if the function is a one-to-one mapping, then the function has an inverse function, which we call the x equals to f inverse of y. So x equals to f inverse of y means that we can, so for here, in this example, x is a variable, right? X is the independent variable, and y is a dependent variable. So the value of y depends on the value of x. But for the inverse function, we can reverse the relationship between x and y. So x is a function. So in the previous example here, so y is a function of x, but we can also write x as a function of y, right? Since they're one-to-one mapping. So we can write y as the independent variable, and x is a dependent variable, right? Because they're one-to-one mapping. So if you flip this figure, right, if you write x here and y in the x-axis, so it's kind of like you flip this figure. And so if you flip that, it's again a function, right? But so this is called inverse function of y. But if you flip this quadratic function, it's kind of like this, right? So for sorry, this should be x, this should be y. So for each y, you have two values of x associated with the y. So this is not a function. It's not a function if you flip x and y. So that's why this kind of quadratic function, they don't have inverse function. Since if you flip the shape, if you flip the function, then it's not the function anymore. But for the linear function like this, even if you flip this line, it's still a line, right? So this is called inverse function. You write x as a function of y. So here, you write y as a function of x. So this one-to-one mapping, this property, is a unique property to strictly monotonic functions. So only strictly monotonic functions have inverse function, right? Because only the strictly monotonic functions have one-to-one mapping. So what is a strictly monotonic function? It has two cases. First one we call a strictly increasing function. It means that when x increases, f(x) also increases. For example, here, if we have two values, x1 and x2, so there's f(x2), f(x1). So when x1 larger than x2, so that means that x increases, right? f(x1) should also larger than f(x2), right? So as x increases, the y value should also increase. So this is called strictly increasing function. It's strictly larger than. Here is strictly larger than, right? And then second is called strictly decreasing function. So that means that when x increases, the value of y decreases and strictly decreases, right? So there's a smaller sign here. So this kind of example is like for a downward sloping curve, right? So when x increases, y decreases. So only these two kind of function, strictly increasing or decreasing functions, have the one-to-one mapping and have the inverse function. So for example, there's a linear function, y equals to 5x plus 25. And we want to find out the inverse function of that. So first we need to verify that this is actually a monotonic function, right? Strictly monotonic function, right? Because if you plot this in the curve, so it's just like this, right? It's a straight line and upward sloping. The slope is 5 and the intercept is 25. Right, so this is a strictly monotonic function. So it has inverse function. And the inverse function, the form is really simple to find that. We just write x as a function of y. Right, we just solve x or isolate x from this function. So this is just a y minus 25 equals to 5x, right? And then we divide 5 to both sides. Oh, sorry, 5x over 5. So this is x, right? So x equals to 1 over 5 times y minus 5, right? We just solve x from this function. And so this is a form of the inverse function, which is really simple. So if the function has an inverse function, then we can apply this kind of rule of differentiation. So the dx over dy, or the derivative of the inverse function, is just 1 over the derivative of the original function. So for example, y equals to x to the 5 plus x. So this is a strictly monotonic function, right? When x increases, y also increases. I want to find out the derivative of the inverse function. So by applying the formula, it should be 1 over reciprocal of the original derivative. So the original derivative should be 5 times x to the 4 plus 1. Okay. So here you just need to pay attention that only strictly monotonic functions have inverse functions. And all the other functions, they don't have inverse function. So the last part is partial differentiation. Right. So first, let's talk about what is a partial derivative. So suppose we have a function like this. Y equals to f of x1, x2, x3 to xn. So y is a function, but it has a lot of variables. Right? It's not like fx, and x is the only variable. But y has a lot of variables from x1 to xn. Right? So that means that all the variables can affect the value of y, not only x1 or x2 itself. And all the x's are all the independent of one another. So they're independent of one another. And the partial derivative means that all the other independent variables are held constant, but you only take the particular derivative of xi. So this means that, for example, we want to take the partial derivative of y with respect to x2. So in that case, you keep all the other variables as constant. Right? You don't change the value of all the other variables, but you only change the variable of x2. Right? You add or subtract just a little bit from x2, and you see how the change, how the y will change. Right? So this is called partial derivative. So the notation for partial derivative is partial y over partial x. So this sign means partial derivative, right? It's different from dy over dx. Okay. So for partial derivative, we use another sign, the thing, to describe that, right? Or we can also write this or simply f x1, right? F x2. So this means that we take the partial derivative of function f with respect to x1. So for example, f1, which is defined to be partial y over partial x1, is just a limitation when delta x1 approaches 0, the value of delta y over delta x1. Right, so y is a function of all the kind of variables, but we keep other variables the same, and it doesn't change that. But we only change the value of x1, and to find out the impact on the rate of change of y. Right. So this is called partial derivative. So suppose we have a function y, and it has two variables, x1 and x2. And the function is as this. So we can see that there are two variables, x1 and x2. Both of them will affect the value of y. And suppose we want to find a partial derivative of partial y and partial x1, and partial y over partial x2. So this is just defined to be f1 and f2. Right? So the way we do this is that, for example, when we are calculating the partial derivative of x1, we treat x2 as constant. Right? We just regard x2 as constant and to take the derivative. So for example, the first term, 3x1 squared, the derivative is 6x1. And for the second one is x1 times x2. But we are talking about the partial derivative of x1. So we don't care about the x2. No, we just treat x2 as constant. So the derivative of x1, x2 is just x2, right? So it's just like the derivative of this x1 and x2, partial over x1 is just x2, because we treat x2 as a constant. So a constant times x1, partial x1, you just c, right? Just a c. So we treat x2 as constant. And so 4 times x2 squared, because x2 is a constant, so the derivative of that with respect to x1 will be just 0, right? Because it's just a constant, right? You take the derivative of a constant, will always be 0. So this is just a partial derivative of x1. And for x2, so 3x1 squared, there's no x2 in this term. So it's just like a constant when we are talking about x2. So the partial derivative of this one is just a 0. And for x1, x2, the partial derivative of that will be x1, right? Because x1 is just a constant here. And for the last part, the partial derivative of that will be 8 times x2. So if you want to find out the specific value when x1 is 1, x2 is 3, and then this is a partial derivative with respect to x1, right? It's this function. So what we're going to do is to plug in the two numbers and find a specific value. So this is 6 times 1 plus 3, which is 9, right? Because partial derivative is also a function of the two variables. So if you want to find out a specific data point or specific value, we need to plug in the specific values of the two variables. So let's see an example here. Y equals to f of uv, which is this. I want you to find a partial derivative of the two. So we can also write the partial derivative as f of u, fv. So here, because it is a multiplication of two functions, so we need to apply for the product rule right above. So at first, for u, we first take the derivative of this one, right? The first function. So this is 1. And then we don't change, we just multiply the original function of the second one. And then plus the original form of this one, and we take the derivative of the second function with respect to u, and we treat v as a constant. So this is just a 3, right? And for v, we did the same thing. We first take the derivative of this function with respect to v, and we treat u as a constant. So the result is just a 0, right? Because there's no v here. And then the same, and the same. And we take the derivative of the second function with respect to v, and we treat u as a constant, right? So this is just a 2. And so if we want to find out the specific value when u equals to 2 and v equals to 1, and the partial derivative of u, so then we use this function to plug in the value of u and v and find the result. So here, we use the second function, plug in, and find the result. Right. So partial derivative is also a function of the two variables. So if I want to find a specific derivative in a data point, we need to plug in the specific two variables and to find out the value of the partial derivative. Okay. So if I change the function as u plus 4 over 3u plus 2v. So in that case, that is a quotient of two functions, right? So when you use a quotient rule and apply the quotient rule, and we treat the other variable as constant when we are talking about the partial derivative of one of the variables, right? So the basic idea is just when we take the partial derivative of one of the variables, we treat all the other variables as constants. And when we take the derivative, we just treat them as constants. Right, so that's the basic idea.